Alright, so number 7 on the practice test says that you should predict the products of the following reaction. Oh, let me get down where you can see it. Balance the equation if a reaction occurs. Include all the physical state symbols. If the reaction does not occur, write the correct symbol. If there is a reaction, and if there is an ionic equation, write the complete and net ionic equations as well. And it gives you these two reactants. Now, apparently I need to add that this should be occurring when there's water around, because I didn't put that in there. In the statement anyway. So we get NH4, 2, CO3, and you've got that should be C little o. Hope I got room to put it in here now.
I did that too the first
time. And then, alright, so that's what it gives you. So, all ammonium compounds are always soluble, so this is going to be aqueous. Sulfate compounds are mostly soluble. There's a few exceptions. Cobalt-3 is not one of them, so this is going to be aqueous. So if a reaction occurs, this is double replacement. And that's because we have two ionic compounds. Another way to think about that is two-part compounds. You've got a polyatomic ion here and a polyatomic ion here, monoatomic ions and polyatomic ions. So those ionic compounds, actually this is positive and negative, positive and negative. So if a reaction is going to occur, this ion here, the ammonium ion, is going to join up with the back of this one, this sulfate ion. And what we're going to start with is just by simply writing them down like this. And we're not going to balance the formula. We're just going to put down the two separate ions. Okay? We're not going to put their charges on there because what we want is a compound formula that is balanced when we're done. Then the front part of this is going to join up with the back part of this one. So we'll have cobalt and a carbonate. Now, before we do anything else, we really would save ourselves time if we'll figure out the physical states. The reason for that is that in order for a double replacement reaction to occur, at least at this point in time in your chemistry career, you need to have a driving force. And for double replacement reactions, the driving forces require that you have a certain physical state of product. Water is going to be liquid. If you form water, that's a driving force, but there's no water here. You can form a gas, but the only thing that makes a gas is carbonic acid, and you don't have that here. So the only driving force that remains is a solid, and so for that we've got to figure out whether this or this is going to be a solid when we're done. So ammonium compounds, as we said before over here, are always aqueous, so this is not going to be a solid. So unless we have the formation of a solid for this compound, we're not going to have a driving force for the reaction. Well, carbonate compounds are, Somebody a question? Carbonate compounds are almost always insoluble. There are a couple of exceptions. Cobalt-3 is not one of the exceptions. So this is our solid, and there's our driving force. Okay? All right. Now we need to balance the formulas. We have to balance the formulas before we can balance the equation. So NH4, ammonium, has a 1+ charge. Sulfate has a 2- charge. So for this formula to be charge balanced, I need 2 of these 1+ charge particles to balance out the 2- charge here. So the formula then for this compound is going to be NH4 subscript 2 outside of parentheses SO4. Okay? Over here, cobalt is one of those transition metals, and it's not right on the ends of the transition metals, it's in the middle of the transition metals, so we don't really know what its oxidation number is going to be. We need to figure out what the oxidation number is for this cobalt to know what this one should be. So we know that sulfate has a 2- charge, we just said that. and we have 3 sulfates. Since we have 2 cobalts, I need a charge on the cobalt that will allow us to completely cancel this total of 6 negative charges on the sulfates we have here. 3 times 2 negative, that's 6. So the only charge on a cobalt that will work here to have a neutral compound is a 3+. And that's how we know that the cobalt over here is going to be 3+. So cobalt then is going to be 3+. Carbonate is going to be 2 negative. So we need to have 2 of these and 3 of these to have a balanced formula. So we'll have a subscript 2 here, and we're going to have a subscript 3 after parentheses following the carbonate. Now we're ready to balance the equation. We've got the formulas balanced. And guys, once the formulas are balanced, you can't touch this. You can't put coefficients in the middle of it, right?
Can't touch this.
Alright? Can't touch this.
Can we just watch that whole video, please?
No.
Why not?
I'm just not going to do that. Alright. I don't have it recorded, so those of you who might be watching this at home, I'll play just a tiny little clip of an old song called Can't Touch This. Okay. Or maybe you heard the sound of it. I don't know. Alright, so we're going to write down all of our elements here for our atom inventory. What now?
Can we please watch that video? We all know the song. Like, word for word.
I'm not going to take time to do that right now. We've got a lab. We're going to blow something up. Let's get on and do that, okay? If we get to it today. We've got to cover all the questions first. I hear you. All right. So, how many nitrogens? 2. There's a 2 outside the parentheses. That's multiplying everything inside here, including that 1 nitrogen in the ammonium formula. So that's 2 nitrogens. Hydrogens? 8 hydrogens. Carbons? 1. Now, oxygens are going to be a bit complex. I like to make sure I'm careful with it by writing out a little math equation out here. I have 3 oxygens in this carbonate. Over here I've got 4 oxygens in the sulfate ion times the 3 that's outside the parentheses. So that would be 12. So I have a total of 15 oxygens. Yeah, that's right, 15 oxygens. Okay. How many cobalts? 2. How many sulfurs? 3. Okay. Over on the other side, I have 2 nitrogens. How many hydrogens do I have? 8 hydrogens. Well, I'm sorry you don't like my 2's, but you know what it is. All right, how many carbons? There's 3 of them. There's 3 outside the parentheses, multiplies everything inside, and in a carbonate ion, we only have 1 carbon in the ion. So that's 3 carbons. 3 times 1 is 3. All right, here we got the oxygens again. Those are going to be complex. I have 4 oxygens here, plus how many oxygens? 9. So I have a total of 13 oxygens for the moment. How many cobalts? 2. How many sulfurs? 1. All right. We want to save oxygens. We want to balance those last and balance the hydrogens next to last. So let's see. I guess we can start with the carbons then. Since I have 3 carbons on the right and only 1 carbon on the left, I cannot change the formula. I can't stick numbers in the middle of it because once the formula is balanced, alright, can't touch this. So, I need a coefficient of 3 out in front. Then that's going to change the number of nitrogens hydrogens, carbons, and oxygens. Alright, so we now have 2 nitrogens because of this 2 outside the parentheses times 3, that's 6. I have 4 hydrogens times 2, that's 8, times 3 is 24. I have 1 carbon here, times 3 is 3 carbons. I have 3 oxygens times 3, that's 9, plus the 12 I have over here, 4 times 3, 21 oxygens. Okay? Alright, so now we've upset the balance of nitrogens. We can fix that. Since I have 2 nitrogens on this side, and there are 2 nitrogens in this formula, the only way to get 6 is to multiply the whole formula by 3. That'll give me, it's going to change nitrogens, hydrogens, sulfurs, and oxygens. Okay, so I have now 6 nitrogens. 4 times 2 is 8, times 3 is 24 hydrogens. Okay, and let's see, oxygens. I have 4 in this part of the formula, this sulfate part of the formula, and then times 3 is 12, plus the 3 times 3 are 9 here, so that's 21, right? Okay, 4 in the sulfate times the 3 is 12. The 3 in the carbonate times the 3 is 9. 12 plus 9 is 21. And then I have now 3 sulfurs. And I think I've balanced everything, right? So that's how you get a balanced equation. But the problem then says go on and write a complete and net ionic equation. In a complete and net ionic equation, you have to identify all of the aqueous ionic compounds and split them up. You don't split up anything else but aqueous ionic compounds. Okay? So this first one here is ionic, and you can know that easily by the fact that there are polyatomic ions in here. Here's an ammonium polyatomic ion. Here's a carbonate polyatomic ion. And it's aqueous. Because it's ionic and aqueous, it's going to split up. So here's our ammonium. Now, if you didn't know ammonium had a plus charge, well, you just got, well, in this class, you've got to memorize it. I'm sorry. Okay, it's one of those things you're supposed to know. Now, we need to figure out how many ammoniums do I have? How many? 6. I've got 2 because of the 2 outside the parentheses, times the 3 of everything. Okay? And what physical state is this ammonium in? Aqueous. Alright, so I've also got this CO3. We already figured out that the CO3 has a 2 negative charge. How many of these carbonates do I have? 3 of them. And what physical state? Aqueous. Alright, then we get to this, the cobalt-3 sulfate. There are cobalt ions here. We already figured out that it has a 3 plus charge. And how many of these cobalts do I have? And its physical state? Aqueous. We can only split it up if it is aqueous. So, somebody had a question? Okay. Then we have sulfates. We've already figured out sulfates have a 2 negative charge. How many sulfates do I have? 3 of them. And the physical state is aqueous. Now we come to the other side of the equation. I've got ammoniums. And I have 6 of them. They're aqueous. and I have sulfates, and I have 3 of those. Oh, I didn't put the charge on there. And that's aqueous. And then I have a solid cobalt-3 carbonate. And that doesn't break up, because for it to break up into ions, it must be ionic and it must be aqueous. Okay, so there's the complete ionic equation. Now, to get the net ionic equation, we just need to take out anything that's exactly the same on both sides. Okay? Those are the guys that are spectators. They're called spectator ions. So I have 6 ammoniums over here and 6 ammoniums over here. We're not going to keep ammonium. They're just hanging out watching. They're not playing. Okay? They're not in the game. I have 3 carbonate ions with a 2 negative charge that are aqueous, but I don't have a carbonate that has a charge or that is aqueous over here. So the carbonate stays. It's in the game. Alright, I have a cobalt. I have 2 cobalt ions with a 3+ charge. They're called cobalt 3s. Over on this side, there's no cobalt with a charge. The only cobalt is in a compound that's solid, and it doesn't match the aqueous over here. So this cobalt is in the game. It stays. Alright, now, I have 3 sulfates over here, 2 negative charge aqueous, and exactly like this, they are exactly like this one. So they're just hanging around watching. They're not part of the game. They're just spectators. It's called spectator ions. We're going to leave them out. Over on this side, we've already said we're going to eliminate the ammoniums and the sulfates. The only thing left is this. Whoop. And there's your net ionic equation. Okay? That makes sense to everybody?